All right, our short lesson today is going to be on the idea of using linearization to estimate values for functions by using the equation of the tangent line, and kind of a notation that's going to be very important for our second half of calculus, which is on integration. So we're going to jump right in and do a quick little short lesson on a nice easy topic for your snow day lesson. All right, so what we're going to do first is we're going to take a look at linear approximation. And it is, as the notes say here, it's pretty easy to do. We're basically going to say that we're going to be looking at a function that is differentiable. Now, the important thing about the differentiability is that we want to kind of have this idea that if you're differentiable, then it is continuous, right? Consequence of being differentiable. And the other thing is that it is also continuous and it has no cusps and no unusual steepness. And that's going to be important because what that tells us is that it's going to be locally linear. And what that really means is that the tangent line is going to be a great approximation for function values that are fairly close to some value x equal to c. Okay? So the idea here is, like, here's a picture example. If I wanted to approximate the cube root of 70, which really at this point what I know about this is that it has to be between 4 and 5, because I know that the cube root of 64 is 4. I know that the cube root of 125 is 5. So since 70 falls in between 64 and 125, then we know that we're somewhere between 4 and 5, probably closer to 4. But I'd like to be able to come up with an approximation for it. So what we're going to do is we're going to use what basically a center. So we're going to use this 64 because that's closer to the 70, and that's going to be our x equal to c. That's going to be our center of the approximation. And the reason that we want to use that is it's easy to calculate. I know the function value's point, that is right there. If I were to ask what this point is on the curve, it would be 64 and 4. So I have the point. I can very easily find the slope using the derivative. We can calculate the derivative over here. That's going to give me the slope. I can write the equation of this tangent line. Okay, so we'll take a look at the tangent line coming in here. And so I would get the equation of this tangent line coming in. Okay. Now 70 is right here, and if I look kind of right here where the 70 point on the function and the point on the tangent line are, you can clearly see that they are very close to each other. I can't even actually see the difference between them given how close they are on this curve, that it's fairly close. We'll talk a little bit in a second about whether or not we have an over or an underestimate, but the idea is that at 70, if I want to estimate f of 70, if this was my function f of x, if I want to approximate that, I want to know what this function value is right here, I can essentially use the tangent line's function value as an estimate. And that's really all linearization is. And the only thing it requires is that your function be differentiable at your center of your approximation, because we don't want to have any cusp or unusual steepness or things that are going to be going on. Now in this example that I'm using for the first one, kind of how far off we're going to be is going to be a really good estimate. It's not always a great estimate, depends on what the function is doing. If the function was curving up fairly steeply from the point and you go a certain distance away, you can see that you can start to have larger and larger error. So there's one thing that we want to talk about, and this is kind of a gray area in this idea of approximation, is that we want to be within the neighborhood of the center. You want to go a certain radius in this direction and a certain radius in that direction, and you want to stay within the neighborhood because you're trying to keep your error, how far off the function and the tangent line are, to be fairly small. And some functions you can go, like on this one, we're actually going 6 units away in order to estimate this 70, but there will be some functions where going even maybe a half a unit away is going to be too far away. So you kind of have to look at the function and see how fast it's changing to kind of get this idea of what our error is going to be. And we are going to look at what the actual error represents and kind of like a percent change and how far off you are as a kind of a measure of that. All right, so let's just come down here to example 1 and go ahead and talk about just working through the problem, what they would expect to see. All right, so I want to approximate the cube root of 70. So it's using a tangent line approximation. We're going to center it at x equal to 64 because that's the closest perfect cube root to 70. We're going to define our function, f of x, equal to the cube root of x. Okay. And then we're going to let your x equal to c be x equal to 64 be your center of approximation. And then the first thing you're going to do is we're just going to find the equation of the tangent line. We already, bringing down from above, we have the point 64, 4. I can figure out my slope by using the derivative. So the slope is going to be, find our derivative, f prime of x is going to be 1/3 x to the negative 2/3. Okay. And so we can go ahead and calculate our slope at the center of approximation. So f prime of 64 is going to be 1/3 64. Let's go ahead and do 1 over the cube root of 64 squared. The cube root of 64 is 4. 4 squared is 16, and then I get 1/16 times 1/3, which I believe is 48, 1 over 48. Now the slope that you have is actually a good indication of if you're within the region. I mean, because clearly if my slope is 1 over 48, if I go up 1, I have to go over 48 to get to the next function value, and I'm only within 6 away. So that's kind of a good indication that this is going to be a good approximation for our actual value for the cube root of 70. All right, so we're going to find the equation of the tangent line. Equation of tangent line. Okay, so y equals, we can use our Taylor form. Just going to go ahead and do our slope, 1 over 48 times x minus 64 plus 4. Now, one of the things that we do, because we are doing a linearization, and a lot of times your function you've already named as y, we're going to give this a different name. We're going to call this L of x for the linearization for the function, or the line that approximates the function, whatever you want to think. So we give this a name so that we're going to be able to refer to it. And then what we're going to do, kind of the work that you're going to show for them, is you're going to say that since you've defined f up here, you're going to say f of 70, which we could say is the cube root of 70, is approximated, do not put in equals here, it's approximated by L of 70. So you can basically say that I am going to get an estimate by using this linearization. This is why we rename it with a new name, so we can kind of put it together in this little statement that says this is what I'm calculating, here's the exact value, and I'm going to approximate it with this. So then we come in, you simply plug in 70 minus 64 is 6. 6 over 48 is 1/8. 1/8 plus 4 is 4.125. So this is not the exact value of it, but it is an approximation for this function value. Now, kind of going ahead and kind of thinking about it, we do have the calculator, so we can actually kind of see what kind of an estimate this is going to be. And kind of while this is coming up, I might want to ask this question: how could we tell whether or not this is an over or an under approximation? Now, clearly I can look at the picture up here and say that based on this, we can see that the function itself is concave down. And because it's concave down, that means the tangent line is always above the curve, okay, because it curves down from its tangent line. So if you were going to say, what is this? You would say this is an over approximation of what the actual function value is, because the function curves down from the tangent line. Now, kind of in work that you would show for this, obviously, you can't really just go by picture. You have to use your calculus. We would need to show, I'm not going to do it in this example, I'll do it in a previous one, but I want you to say, show that the f of x is concave down, and we might want to remind ourselves, how do we show that a function is concave down, we look at the second derivative, and we want to show the second derivative is less than 0. I will leave that for you to do kind of as a little quick review on this, because that's just kind of old hat stuff to us right now. And what we want to basically then be able to say in answering the question, you would say that L of 70, which was our 4.125, is an overestimate of the cube root of 70 because f of x equal to the cube root of x is concave down since f double prime of x is less than 0 for all x greater than 0, which is what you should find as your conclusion when you do this little part up here in the circle. All right, and so that's really basically all linearization is. It just says, hey, I'm going to use the tangent line. I'm going to use the tangent line to approximate. As long as the function is locally linear, which basically means differentiable, no unusual steepness, no cusp, and continuous, then we can use this as a linear approximation. Now, kind of the last little part of this example that we're going to look at is it also has you here kind of looking at the secant line and using the secant line to approximate. Now, we won't do this pretty much very often, but I wanted to show it to you because the kind of the nice thing about the secant line approximation, and I'm going to exaggerate the curve just to kind of show you. If I have a tangent line of a concave down curve, the tangent line is always above the curve, an overestimate. If I look at a secant line using this point and one over here, the secant line over here is always below the curve. So if I'm actually trying to find an estimate for something right here, I have an over approximation with the tangent line, I get an under approximation with the secant line, and then that kind of gives us a upper and lower bound for the actual value that you're looking at. So on this, notice that we decided to use, it's giving you to use x equal to 64, which we already know is the point 64,4. And then we're using 125, obviously, because 125 is a nice cube root, and the cube root of 125 is 5. And there's no calculus involved in this. I just basically go the slope of the secant line is going to be your change in y, 5 minus 4, over your change in x, 125 minus 64, which is going to give me 1 over I think this is 61. So the equation of my secant line, again, you're using the equation in order to get the estimate. Let's give it another name. Let's call this g of x. Call it s of x, whatever you want for secant line. Actually, I like s of x better, so I'm going to do s of x. So s of x, the equation of your secant line, is going to be your slope, 1 over 61. I'm going to go ahead and use this point, although I could use either, but I'll use this one, closer to 70. X minus 64 plus 4. And so if I was going to calculate, I want to know what f of 70 is, and I'm going to basically be trying to estimate the cube root of 70, I can approximate it with s of 70. And again, this is now going to be an underestimate. And so I basically plug in my 70, 70 minus 64, 6. So I get 4 and 6 61st, which I don't really know exactly. But what I do know, based on the information that we have so far, is that the cube root of 70 has to fall between the overestimate from the tangent, which was 4.125, and the underestimate from the secant line, which is 4 over 6 61st. And so then just to verify this for us, we'll just go ahead and kind of show that this is working for us. 4 plus 6 over 61 gives me this number. And my cube root of 70, so 70, oops, I have a little bit too many 7s in there. Got a little excited. Delete, delete, delete. 70 to the 1/3. I don't know why my calculator is having little extra issues here. It wants to give me extra things when I hit enter. All right, so there's the actual value. Well, actual rounded to as many decimal places as your calculator will give you, and then our 4.125. So you can kind of see that the actual value falls in between the underestimate and then our overestimate of 4.125. It's a little closer to the tangent line, but you can't really say, you don't really know which one's more accurate. But pretty much, this was just kind of an illustration. We're going to be using the tangent line as our approximation each time. All right, so taking a look, I'll leave this for you. This kind of just recaps what we just did, that we want to find the equation at the center at some point. That's a nice point. We make sure we rename it. That's going to be important. You plug your value into L of x, writing your notation very carefully because you want to make sure that you are doing it's an approximation, so you want to make sure you include that. And then you can determine over or under approximation by examining whether your second derivative is less than 0, causing the function to be concave down, or your second derivative is greater than 0, causing your function to be concave up. All right, so we'll do one more example. I'm going to leave the next example 3 for you to do. But I want to estimate the fourth root of 17. So I'm going to come in and go, I want to calculate the fourth root of 17, so I am going to make my function the fourth root of x. So I'm going to use the tangent line. Now I go, okay, fourth root of 17. What do we know about fourth root of 17? What nice, perfect powers of numbers, when you have like a fourth power or something, is going to give me something close to 17. So we know that it's kind of in between the fourth root of 16. The fourth root of 16 is 2. And smaller than, so we'll say it's in between this, and the next one up would be 3 to the fourth, which is the fourth root of 81, which is where we have our 3. So it's somewhere in between 2 and 3. That's the best I can do without calculus. So now we're going to do this local linearization. My fourth root of x, we know, is going to be differentiable for x greater than 0. So we know that we can go ahead and kind of use this local linearization, differentiable for x greater than 0, because it's an even root, so we know basic powers, functions, and how they're differentiable. So I'm going to go, my point, I'm going to use the closest one, let's do 16. So we're going to have 16.2 be the point or the center of approximation. So we're going to approximate near x equal to 16, okay? Or c equal to 16 if you want to use c for center. I need to find my slope. My f prime of x is going to be 1/4 x to the negative 3/4. And if I want to, you can rewrite this as 1/4 cube root of x to the 4th. So we can go ahead and calculate our slope at 16. Our slope at 16, I'm going to do the cube root first. Let's see. 1/4, the cube root of 16 to the 4th. It's not going to work out, but I'm going to do the 4th here. Let's do powers of 2 and then come back and approximate what this is. 16 is 2 cubed. I'll make it the easier way because I don't have a calculator, obviously, to approximate. So the cube root of 16 is 2 to the 4th. To the 4th is going to be 2 to the 16th. And then so we could simplify this down. You know, it's a good thing, you know, when you look back at something, I rewrote this in the wrong fashion. It's the fourth root. I was like, why is this not working out for me? It's not working out because I wrote my roots wrong. So coming back and fixing that, it's the fourth root of x cubed. And so I'm doing the fourth root of 16 cubed. The fourth root of 16 is 2. 2 cubed is 8, so I have 1/4 times 8, which is 1/32. There we go. I was like trying to figure out why that wasn't working out to a nice number when you pick these examples. So I get this. I'm going to write my equation of the tangent line, and I'm going to go ahead and just call it L of x for the line so I can refer to it. I would have my slope 1 over 32 times x minus 16 plus 2. And then remember, when you go to write this, you want to make sure you do this in nice notation. We're calculating f of 17. The fourth root of 17 is what I am trying to approximate. So then I go little squigglies. It's going to be the approximate with your L of 17. So we go ahead and then we just basically plug and chug. We put in our 17 minus 16, which is 1, and we get 2 and 1/32. And then we have to answer the question about whether or not this is an over or an underestimate. So I'm going to go do all the work for this one just to kind of show you. We're going to come to the second derivative of x. So everything over here is basically to answer the question over or under. You're not allowed to go by, I know that function is concave up or concave down. You must use calculus. So we're going to go for the second derivative. The second derivative, kind of coming right here, would be negative 3 over 16 x to the negative 3/4 minus 1, negative 7/4, which is going to be negative 3 over 16, fourth root of x to the 7th, and that second derivative is going to be less than 0 for all x greater than 0, okay? Because you would have a positive number here, and then negative divided by positive is negative. So we would say that your L of 17 is now what would we conclude about our function based on this? If you have a negative, we have a concave down f of x. And if f of x is concave down, then this L of 17 is an overestimate of the fourth root of 17, because f of x is concave down. And the reason it was concave down was because the second derivative at 17 is going to be less than 0. Right? And so that's pretty much all linearization is. I'm going to leave example 3 as something for you to work on your own. We'll kind of check that when we come back into class. Because this one's pretty easy. I'll just help you set it up. Your f of x would be x to the 5th. Your point would be 3, and then whatever 3 to the 5th is. All right, down here, I'll help you set up example 4. You're going to do the same thing. I want to approximate this. So I go, what's my function going to be? I'm going to use f of x equals the natural log of x. And then I go, well, what is a number close to e to the 10th plus 5 that I actually know the natural log of? And hopefully somebody out there is shouting e to the 10th. And because you know what is the natural log of e to the 10th, it is 10. Nice powers of e thing. So I would use that as my point. And so you're going to run through and do example 4 as well. All right, so now what we want to do is we want to come back and we're going to talk about some new notation. And this is kind of going to be the basis for the second half of the course, which is on intervals. And this notation is based on Leibniz's notation for the derivative. We're coming back to this dy dx, which is your derivative of y with respect to x. That's kind of how we've been treating this or stating this for our derivative, our instantaneous rate of change. However, what Leibniz actually did is he didn't treat this as one quantity. He actually treated the dy as one thing, okay? And this is called the differential of y. And then he treated the dx as a separate quantity, and that was the differential of x. And the idea is that you kind of were thinking of this as, we were doing our little limits and our approximations, that we were doing delta y over delta x. And that if we were to actually measure the change in y over the change in x, we could estimate what the instantaneous rate of change is. These two things here are measurable quantities that we could actually calculate from the function that we were looking at. And then what we did is we started to take limits and we let them go to teeny tiny, immeasurably small values. And that if I make these small enough, then by doing the limit, then they would turn into the differential of y over the differential of x. They would turn into the derivative by taking the limit as, say, delta x approaches 0, which also causes delta y to approach 0. Um, what Leibniz would call this is infinitesimally small. So he actually called this the calculus of infinitesimals, which is this idea that these are two separate quantities, both heading towards 0, but maybe at different rates, which would allow us to calculate the limit as, say, delta x goes to 0. All right? And so they are change in respective values. Now, the other thing that we want to kind of take a look at is this little diagram over here. And this is what we're kind of representing over here. That if with my linearization, I have a center of my approximation. Here's my x equal to c that I was using for my center. And that if I were to find the tangent line, and how do you find the equation of the tangent line? You found the slope of the tangent line, and the slope of the tangent line is this dy over dx, right? And since it's the slope of a tangent line, we can treat this as the change in x is this way, and then the change in y is the distance from your point P up to another point on your function, this r right here, okay? Now, if you think about what would be the y value of this point, just kind of coming in over on this side, it would be f of x plus delta x. That would be your y value up here. And then what would be your y value for p? Your f of x. F of x would be the y value down here for p. And then your differential in y is simply the difference between f of x plus delta x over minus f of x, which is starting to look a little bit like the derivative. And so that's the idea, is that the differential is the slope of the tangent line, and we can treat them as separate quantities as such. And then the delta y and the delta x, these are the actual change in y and change in x that the function is going through to this point. And that's kind of the relationship that we have for this. Now, the differential form is nothing more than saying, hey, if I can treat these as two separate quantities, then I can separate them, multiply both sides by dx, and write the derivative written in this form, and this is called the differential form. Okay, and then, of course, the other thing that I want to add on to this little picture up here is this difference right here between what the differential is and delta y. That's essentially looking at your error in this. How far off is the estimate that we were coming up with from the actual value by looking at that error right there. All right, and so first thing, let's just practice notation. The notation itself is super easy. You basically just want to come up and be like, okay, I know how to take the derivative of this using the actual nice notation. We've been doing related rates for a while, so we can do dy dt equals the derivative of 2t cubed, which would be 6t squared, plus nt minus 3. That's the old way of doing it. The new way of just writing it as a differential, you simply say the differential with respect to y. When I start splitting them, it's not the derivative anymore. This is the differential with respect to y, the differential of y. And then we just do it 6t squared plus 10t minus 3 times the differential of x. And you just write it in that notation, and that's your differential form. So the differential form is super easy. Pretty much just use the dy dt or dy dx notation, and then just move it to the other side. You can actually skip this step and come straight to here. If I know I want it in differential form, we don't even have to write the step here. We are good enough that we can just skip right down to the bottom. So for b, let's go ahead and do b. I was doing the differential form, so I go, hey, dz. Now technically it's with respect to x. I'm just going to remember that after I take the derivative over here, I'm going to put the differential of x over on this side. And then so the derivative, a little practice, product rule, little chain rule going on. The derivative of this would be x cubed times the derivative of sine, which is cosine 3x, times the derivative of 3x, which is 3, I'm going to write it in front, plus my sine of 3x times the derivative of x cubed, which is, and actually I'm going to write that in front just to make it look a little nicer while I'm here, the derivative of x cubed, which is 3x squared. And that would be your differential form. Again, fairly straightforward, similar to what we were doing before. And then one last one, let's go ahead and do C here just to get that example in. Our differential form for this would be the derivative differential of m would equal, what's the derivative of exponential? Itself, 5q squared plus 1, times the derivative of the exponent, which would be 10q, and then we follow that whole thing times my differential in q. Okay, so fairly straightforward, just using the differential form, fairly easy to come up with. And then other than just a change in format, what is an application that we're going to use this for? What we're going to do is this idea of this linear approximation, that if delta x is small enough that the change in y approximates the differential in y. It's not exact, there's going to be some error, but if you are small enough, then we can basically estimate using this approximation. And so what we're going to do, we're going to look at a problem like this. Let's take a look at example 6 and kind of work through how this is going to be looking at. And this is a good kind of production problem. A lot of times when you're producing machined parts of some sort, there's usually going to be some type of an error in your product that you're creating. And so they're making this little spherical bearing, and then they measure it after they create all these little round metal bearings with a caliper. And they want the radius, they want it to be 2.3 inches. So they're trying to manufacture it to be 2.3. But then they realize that they're okay as long as, once they manufacture them, that they have a possible error no greater than 0.0001, right? And so the idea is that they're trying to basically figure out the maximum error in the volume given that they're allowing this error in the radius. So the idea here is that what you're trying to do is, let's go back to our volume formula. Alright, so the first thing you do in the problem is we realize that it's kind of like reading the word problem. We're going to have an input variable is going to be our radius. We're interested in the error in the volume based on this. And it's almost kind of like a related rate problem, except we're looking at differentials instead of related rates. So what we're going to say is that we're going to give a volume, V and R are my variables. So the volume of a sphere is 4/3 pi r cubed. Okay. Now what I'm going to do is I am going to take the derivative, not with respect to time, but because I'm talking about an error now, I'm going to take the derivative and write it in differential form. So I'm going to figure out the relationship between the differential of the volume and the differential of the radius. So dV is going to be equal to 4 pi r squared dr. The differential in the volume is going to be 4 pi r squared times the differential in the radius. That's how the differentials are related. And then we pretty much come in here and say that when delta x, or in this case my delta x is going to be delta r, when my delta r is small, okay, and remember delta r, if you go back and take a look at our picture up here, delta r and delta and dr are pretty much the same. That's going to be kind of the key for this. These are always equal to each other, okay? And we pretty much say when delta r is small or dr is small, then we can approximate your dV, your differential in V, with delta y, okay? And that's kind of the key for this entire thing. So when we're going to plug and chug. The differential they gave you for the radius is you want your error to be no greater than 0.0001. So what we're given in the problem is we're going to let our dr be our 0.0001, okay? And then we would say that then our dV is going to be approximately 4 pi r squared times, oh wait a minute, we do know the r, it's kind of like the plug and chug from the related rates. R is 2.3, that's what we want it to be. Okay, so 2.3 is what we want it to be, and then our error in the radius is 0.0001, and so we're basically going to calculate that, and we're going to use this, which is actually your delta y. That's going to be our estimate for our dV. All right, and so when you basically just plug that into your calculator, we're going to get that to approximately 0.0066, and our units are going to be inches cubed. So we basically are looking at when your radius is 2.3 inches, your error or your differential in your volume is going to be about 0.0066 inches cubed. Okay? Now we can actually calculate the error for this as well. Okay, to get this error, we're going to, or the kind of the percent change kind of thing, we're going to take the error that we've calculated, we're going to divide by the actual volume at 2.3, and of course I'm going to multiply by 100, and that's going to kind of give me this percentage of how far off I'm going to be. All right, so we're going to take our 0.0066, we're going to divide by the actual volume at 2.3, so that's 4/3 pi 2.3 cubed, and I'm going to multiply that by 100, and let's take a look at kind of what our percentage is. So pull your calculator out and take care of that. Alright, so I went ahead and entered this into my calculator. Didn't make you suffer through that because my calculator is still having those button pushing issues. So I took the value of dV that we estimated, which is right here, and then I divided that by the volume at 2.3, the actual volume, and then times by 100. So we get a percent error, kind of how far we're off, by 0.013, which is pretty darn close in terms of a percent error, 0.013%. And so that kind of gives you an idea of how we're going to be using these differentials. And again, just to kind of recap where we were in this, you want to do the same thing we've been doing like with the related rates. You're going to figure out your variables. My variables were radius and volume. And the instant in time that I'm concerned with, or what I want it to be, was the 2.3 radius. I wanted my error to be no greater than, the error in the radius to be no greater than 0.001. So that's my differential in R. I find my formula that relates my differentials together instead of my rates. I'm not taking it with respect to time. I get my differential form. I basically plug in the differential for R, the radius that I wanted, and I estimate the differential for the volume, which is going to be our, technically I guess I should have said dV, delta V right here, because Y is V in this problem. So we estimate our differential in the volume by using delta Y. And so basically we come up with that the difference in the Y, the actual difference, that's what this is, the actual difference can be found using the slope of the tangent line, which is where the dV comes in, change in y over change in x in the tangent line. So we are basically doing linearization again. And we can plug it in, we get what our approximate delta volume is, which is this, and then I can calculate my percent error by using this formula. Okay? And yes, and this is the maximum possible area, because the only calculus thing left to do is make sure we answer the question. The max possible error in volume is 0.0066 inches cubed. And again, why was this a max? That would be because in this situation, if we were looking at the formula, we would have an overestimate of our function, or we could do an underestimate if it was concave up looking in, all right? And so in our picture, the actual value and then the dV is going to be in this situation, because our dV is this part. Our dr is going to be here, and then the actual, what actually happened right here is going to be the delta v. And this is what we are approximating with the slope of the tangent line. And so our max possible error, the farthest away I could be, is going to be what the differential in v is. All right, so that's going to wrap this one up. I'm going to put up the worksheet as well for this so that you can begin working on it, and we'll do more examples on this in the next class.